Hi, this is Aaron Jerome at Jerome Electronics. You are listening to a song called The Killer's Boogie Dance, written by Jan Reitman. He's a Dutch composer. And the real fun thing about this dance is to watch a dancer named Steven Sayer dance to this. That guy is a natural dancer and worth looking up. Anyway, we got to get to what we're really here for, and that is AOL Logic Implementation. And that's just, well, you'll see this is a trying to get students to connect ideas to how to make a simulation just before making a prototype. So, AOI implementation. There is a worksheet that I give my students. This is the worksheet that I give my students. And we'll be getting into that in a minute. The point here is that we want to take an idea from our head and work it into a simulated circuit. So let's talk about how you can make a lot of money. Let's say that you have invented the hover car, but you still want the car to run on roads as well as in the sky. So picture this. You're a genius who has made millions from your brilliant ideas. One day you have another amazing idea that you can make more money. Here's the idea. I need my car to start the hover motor if either my car goes too fast or too slow, but not both. So I guess I better go back and talk about this idea. What it's doing is it's saying if you are on the road in your hover car, but you're on the road, not hovering, and you're coming up behind a slow driver, we want to make a sensor that will say there's a car coming up ahead of us and they're going slower than us. And that will automatically turn on the hover motor before we reach that car so we can just go over the car and back down on the road. Now, that works great if our car is going faster than the one in front of us, but we might also be going slower than a car that's coming up from behind us. And so we need another sensor that can sense that there's a car coming up on us. And as they get close, we just hover and they go right under us and then we go back down on the road. Now, I have made the stipulation that not both. What does that mean? Well, it would make sense if there's a car slow in front of us and a car that's fast behind us that we would hit the hover motor. But I said but not both to make this problem more interesting. So that's kind of where we're going with this. So the question is, how do we get from this idea, which we have written down, to an actual prototype that functions correctly? So Here we're going through those steps that we introduced earlier. First, we're going to write down the idea. I need my car to start the hover motor if either my car goes too fast or too slow, but not both. So there are a lot of reasons to write it down. One reason is that it proves you thought of the idea first. You can patent it, and then nobody can steal the money from you, from your idea. So you write it down first. Next thing to do, of course, you have to write it down to be able to capture the idea because we need to identify the input sensors. So I'm actually going to highlight what the input sensors would be in this equation. There is a sensor that says, hey, you're coming up on a car too fast. That we're going to simulate that with just by using a switch A. Or if it's too slow, we're going to be, that means there's a car coming up from behind. And so we want to hover if we're going too slow for the car coming up behind us. So that would be simulated by switch B, but not both. Also, we want to make sure that we identify the output from this idea. Of course, that is the hover motor. The motor is the output. Next, we set up what we know about this circuit. We're going to be using a truth table for that. And so what are we going to need to be able to set up this circuit? I guess I'm jumping to the simulation, actually. The simulation is, we use multi-sim to make the simulation. We're going to need some power, so we're just going to set up, a source of power. That's VCC, 5 volts. And we're going to set up a ground. That's going to be DGND, we'll need a couple of switches. This is everything we know about the circuit right now. We're going to need switch A, which will eventually be swapped out for sensor A, and we're also going to need switch B, which will be swapped out for sensor B. A is if we're coming up too fast on a car in front of us, and B is if there's a car behind us coming up too fast on us. In either case, these sensors will automatically start up the hover motor, which will cause our car to hover, so we can either go over the one in front of us, or the one coming up from behind can go under us. We're going to need an output, which is going to be the hover motor, but we're going to simulate that with an LED because, we don't want to spend all the money until we know that it works. And of course, there's the mystery circuit solution, and we don't know what's in that yet, but we're going to find out real fast. Okay, so what we're going to do, I guess what I need to show you is that if sensor A is activated, it's going to turn on the hover motor. If sensor B is activated, it's going to turn on the hover motor, but both of them will not turn on the hover motor. I guess that's just we're in danger of being crunched between two cars, but it makes it more interesting. So what does the truth table for this circuit look like? Now, you have been given a student worksheet, and I believe I've already put the truth table on it. So what we want to do, though, is we're proceeding into building the mystery circuit solution. So here's the truth table. Maybe. Here's the truth table. And what you want to do is try to work ahead of me on this. From the information we have, the written statement with the output and inputs identified, can you figure out what the outputs will be for this truth table? This is probably a good time to pause the slide. And as we continue, if you understand how I'm doing what I'm going to be doing, try to work ahead of me and see if you can predict what I'm going to do before I do it, all the way through to the simulation of the mystery circuit solution, all the way through to the prototype. There's a truth table. We've got the A column and the B column, and of course it's just a binary count. I haven't put the index column on this, but it is just a binary count, 0, 0, 0, 1, 1, 0, and 1, 1. So we also have indicated what we want for the output. Since we said not both, and since we want 0, 0 to mean that neither sensor has indicated a need for the hover motor, so row 0 is going to be a 0. And that implies that the hover motor is not needed. For row 1, the B sensor has been activated, and that means B is us going too slow. That means we need to turn the hover motor on so that a fast car from California can just roll right under us. And then in the row 2, row 0, row 1, row 2, and row 2 is the activation of the A sensor. And of course, if we're coming up on a car, say from Idaho, it's going really slow, it's going to automatically activate that hover motor. We're going to float right over the top of it and then come back down in front of it. And then, of course, not both. And so if both switches are on, we don't want the hover motor to come on. Probably should, but we don't want it to for the sake of making this problem interesting. So what kind of a gate is that? Well, if you're really sharp, you probably have already recognized that this is an XOR or a XOR gate, an XOR gate, exclusive OR gate, but we're not going to use an exclusive OR gate here. Instead, we're going to pull the term from each one of the rows, and then we're going to OR those two terms together and make an equation. So what might the Boolean expression look like for this problem? Well, remember, we only pull terms when the outputs are 1. So we've got one term there. A is a 0, so that's a not A. And then the vertical line is a multiplier, and then there's a 1 under the B, so that is an is B. Not A, B. is the way that's read. For the next row, that is a 1 in the output. It is not a 0 in the A column, it's a 1, so it's just an is A multiplied by a 0 in the B column, which is not B. Next thing we need to do is combine these two rows, and we do that with an OR gate or a plus. So there's the first term plus the second term, and we made it equal to 1, which is, we should have just made that equal to x, but equal to 1. And this is just everything we've already learned. But the next thing we need to do is use that equation to indicate the mystery circuit solution. So we're going to use each variable and each operator in this equation to build our mystery circuit solution. Okay, making myself a little bit of space to be able to do that. Open up some space in the middle, and we're going to build this circuit. We're going to simulate this circuit. Well, the first thing we're reading from left to right, and the first thing we need to do is figure out how to take switch A and we can use the expression to build a mystery circuit. The Boolean expression tells us what we need and where we need it, so that not A is what we need first. We need to take A and convert it to a not A. Well, that's pretty simple. To convert A to a not A, we're going to need a NOT gate, an O4, an inverter. There it is. I've installed an inverter. Notice there's a little spur coming off of A. We're going to use that later. I just needed a place to attach it. But what we really need is not A. Next thing is a multiplier. Hopefully you can see that little dot there. That just means we're going to use an AND gate. So there's our AND gate, and we got not A going into the AND gate, and we have to AND that with B. So we're just going to tap into B and connect that to the AND gate. The next thing is a OR operator. So we're going to put an OR gate because we're ORing the first term, adding the first term to the second term. So there is our OR gate, and we're ORing that with an A, which is going to be multiplied times B, not B. So we've got to put a NOT gate in here, and there's our NOT B. And that, of course, will equal 1. Now, what have we done? Hopefully, on the student worksheet, you've been sort of predicting this before I have, or at least sketching it in as I have, trying to understand. You can take an equation and use it to build a simulation one component at a time. And this is how we've done it. So, we've used 4 different tools here. The next step, breadboard, using the circuit diagram as a guide, but an even more important skill is to be able to prototype by using the equation. So these are 5 powerful tools for turning your brilliant genius ideas into big money. The written idea, the truth table, from which we can pull out the expression, combine those to make an equation. The circuit simulation can be built from that equation, and either the circuit simulation or the equation can be used to develop the prototype. So the breadboarded circuit. So that's it. Hopefully this has made sense, because we're going to be doing a lot of this in the near future. That's it for now. Stay tuned for another presentation coming up. Thanks for watching.